Okay, so good morning to all of you. So let me thank the organizer at the outset to invite me to this conference and allowing me to speak on this topic, pointwise pseudo-slant submanifolds of a Kenmotsu manifold. So I hope everybody knows about these Kenmotsu manifolds. I will recollect these structures. So what happens whenever we have a submanifold embedded into a ambient space, the connection on the ambient spaces uh, induces a connection on the submanifold. And these two are related by equation number 1 and 2. When you differentiate a normal vector field, you get this formula number 2. And when you differentiate a vector field tangential to the submanifold, you have a formula number 1 known as Gauss formula. The second one is Van Garten formula. These will be our notations. And then there appears the second fundamental form. It's a normal value 2 form on the submanifold. And this is related with the shape operator in equation number 2. And they are related with equation number 3. The shape operator and the second fundamental form are related by relation number 3. These are some basic things, but I am talking about them because the symbols and the nomenclature should be understood. Now, since the Kenmotsu manifold is an almost contact manifold which has a structure vector field, so there is a possibility that the structure vector field may be tangential to the submanifold, it may be normal to the submanifold. In case when the structure vector field is tangential to the submanifold, we have observed that h u xi is 0, as well as the shape operator a n xi is 0. In case when xi is a normal vector field, we have equation number 5. So these are some basic things we need to keep in mind. And when we consider our vector field, now whenever we are dealing with some manifolds, what we do, we decompose phi u and into tangential and normal part. If u is any tangent vector field, we can decompose it into tangential and normal part. The tangential part will be denoted by tu and the normal part will be denoted by fu. So these are some of the symbols. So at every point I can decompose like this, but globally speaking, the T and F will be the one tensor field. One is tangent valued and the other is normal valued. Okay, similarly, we can decompose for any n. If you have phi n will have tangential and normal parts. So the tangential part will be denoted by small tn, and a small fn denotes the normal part. So these are some convention of the symbols that I'm specifying over here. And what we do to begin with, we compute the covariant derivative of the one tensor field T. It is obtained as this expression in number 6. In particular, we can compute delta bar xi tu. This turns out to be 0, and the and delta bar u t xi comes out to be minus tu. These are some easy computation and well known. Okay, now let us come to the distributions. So let me talk about the slant distribution. So if D is a differentiable distribution on the submanifold, then for any u which is independent of the structure vector field, if you look at the angle between phi u and the distribution dp, if it remains constant for every point p and for every vector field u, we will say that distribution is this angle is constant, we say that distribution is a slant distribution. If it is constant only at a point p and it changes on the other point q, then we will say that distribution is a pointwise slant distribution. So the formal language is written over here. So these are the distribution that we will be working with. Okay, Now, then I have talked about if theta is the angle 0, it is 0 for all vector field, then the distribution, slant distribution will become an invariant distribution. If the slant angle is pi by 2, then the slant distribution is in fact phi anti-invariant distribution. We will try to think of a proper slant distributions where theta is different from 0 and pi by 2 respectively. All right. Now there are some well-known results which I need to tell you over here. If you are working in a contact metric manifold, then and the dimension of the M in manifold is 2n plus 1. And there is an anti-invariant submanifold of dimension n plus 1, then obviously xi will be tangent to the submanifold. So this is a well-known theorem which I have specified. Now the converse part, if you are starting with xi to be tangential to the submanifold, then the tangent bundle will decompose into two parts. One is a distribution D and the other is xi. So D stands for the complementary distribution of xi. If it is slant, if D is slant, then we will say the submanifold is a slant submanifold. Xi cannot belong to a slant distribution because we demand in the case of slant distribution that each vector should have a constant angle. So xi, since phi xi is 0, so xi cannot belong to the slant distribution. So this is an important observation. All right. Then proper slant, and some of the observations are proper slant, semi-slant, and pseudo-slant submanifolds orthogonal to xi are non-existent in a Sasakian manifold. So that is why we will be considering non-Sasakian manifolds. More specifically, we will be considering Kenmotsu manifold. In fact, when Steno classified some manifolds whose automorphism groups has the maximum dimension, then there appears classes. So one of the classes is a warp product manifold, and this warp product is look like R product FCM. So what we thought over here, why should not we consider warp product submanifold of a Kenmotsu manifold? So Kenmotsu manifold belong to different class than of the Sasakian manifolds. So, so these are some of the consequences of well-known theorems. So under what condition a distribution is a slant distribution on a submanifold? So there is a well-known theorem which says that if M is a submanifold of an almost contact metric manifold, which is tangent to the structure vector field xi, then M is slant if and only if the following condition is satisfied. That is, T square is minus lambda I minus eta tensor xi, where lambda is cosine square theta. When we deal with the pointwise slant submanifold, this theta is not fixed. At every point, it has a specific value. So theta becomes a function on the manifold. So this is to be kept in mind. Well, when M is a slant submanifold, theta remains constant throughout. Now, BY chain consider generalized version of slant submanifold, and these are pointwise slant submanifold. And the study of pointwise slant submanifold started with a paper by K.S. Park. This appeared sometimes in 2009. I have given in a reference. All right. Now, what he did, he defined a subspace of the tangent space, which he denoted by the symbol MP. So MP consists of all those vector fields which are orthogonal to xi p. So what happens if you have a pointwise slant submanifold, then the theta, then T square, according to the last theorem, will be, if you look at the last theorem, T square will be equal to minus lambda I. Or you can say T square equal to cosine square theta I. So this is same as what BY chain obtained for slant submanifolds. So this is one of the way that K.S. Park has dealt with pointwise slant submanifold. All right. Now we start with, and there are examples. Any two-dimensional submanifold of almost contact metric manifolds are pointwise slant submanifold. And we also observe that the product of Tx and Ty is zero if and only if X and Y are orthogonal to each other. These are some easy observations on a slant submanifold, as well as pointwise slant submanifold. So let me talk of pseudo-slant submanifolds. So pseudo-slant submanifold of a Kenmotsu manifold, or in general almost contact manifold, admits a distribution D1, which is a slant, which is a pointwise slant submanifold, and its orthogonal complementary distribution, which we are denoting by D2, is anti-invariant. So we have written it down like this: is a pointwise slant submanifold if there is a distribution D1 such that its orthogonal complement D2 is phi anti-invariant. That is, this Tm will be decomposed into two parts. Direct summands are D1 and D2. And in this case, to work with these distributions, what we do, we generally decompose an arbitrary vector into three parts, one along D1, one along D2, and the other one along Xi. So we denote these components in D1 and D2 by B and C respectively. So these are some of the convention on symbols. Okay, if the structure vector field is tangential to the submanifold M, then it cannot lie in D1 as I specified earlier, because we demand that the angle between theta u with dp phi u with the distribution should be same. So phi xi being 0, it will always be 0. So it cannot belong to a non-trivial slant distribution. You can also observe that the normal bundle will be decomposed into two parts, into three parts rather, FD1, FD2, and mu. These are some easy observations. All right, so what we observe over here, that this part, the third part of the decomposition, that is mu, we have an observation here in proposition. Let M be a proper pointwise pseudo-slant submanifold of an almost contact metric manifold, then mu is phi invariant normal subbundle if and only if either mu is contained into kernel of eta, or D2, the anti-invariant distribution, is contained into kernel of eta. Then we have certain formulas. And they are first one, in fact, in this proposition, we obtain certain formulas with regard to shape operator, second fundamental form, etc. So these are some useful formula that we obtain over here and make use of them to obtain some geometrical results on pseudo-slant submanifold. So the first result is about the distribution. We have worked out some other formulas also, and these formulas led us to this theorem. Let M be a proper pointwise pseudo-slant submanifold of a Kenmotsu manifold M bar, then the distribution D1 is involutive on M if and only if this condition holds. So this is the condition for integrability of this pointwise slant distribution on a Kenmotsu manifold. Then various other formulas were obtained, which led to the other theorem about the integrability of the complementary distribution, which is phi anti-invariant. This says that M bar be a Kenmotsu manifold and M is a proper pointwise pseudo-slant submanifold of M bar, then D2 as well as D2 direct sum xi are involutive on M. Okay, so this was the consequence, one of the consequence of this theorem was that M be a pointwise pseudo-slant submanifold of a Kenmotsu manifold, then the anti-invariant distributions defined a totally geodesic foliation on M if and only if this happens. This is a consequence of some other formulas. So this is interesting results. So while studying warp products of manifolds, we see whether the first factor of a warp product is totally Jauresic or not. So we have this formula which ensures the totally Jauresicness of the first factor. So this formula will be used while discussing warp products of manifolds. Now I start with W warp product. These are the most general submanifolds. So first of all, let us understand what W warp product manifolds are. So our aim in this section is to study some manifold of Kenmotsu manifolds, which are warp products, and these W warp products, some manifolds, are isometrically throughout. I mean, throughout we will be assuming that our submanifolds are isometrically immersed into a Kenmotsu manifold, and these submanifolds are W warp product. Okay, so all right. So what happens is, if you have two Riemannian manifolds, say N1 and N2 with Riemannian matrix G1 and G2, and F1 is a real valued function on N1, F2 is a real valued function, a smooth function on N2, then the warp product, which we write down as F2N1, product F1N2, is a product manifold which is endowed with a special matrix G equal to F2 square G1 plus F1 square G2. We call this matrix G to be a warp product matrix. So any product manifold of two Riemannian manifolds with this matrix G is called a W warp product manifold, and the matrix G is in fact a W warp product matrix. And to find out some formulas, we consider projections. Pi denotes a projection of N1 product N2 onto N1, tau denotes projection onto the second factor, then G is precisely defined by formula number 10. Now some special cases, if F1 is 1 or F2 is 1 of the function is constant 1, but not both, then we obtain a single warp product. If both F1 and F2 are 1, then we have simply a Riemannian product, N1 product and 2. Usually we call it a trivial warp product. So when a simple Riemannian product of two manifold is also a warp product, but it's a trivial warp product. If neither F1 nor F2 is constant, then we have a non-trivial W warp product. Now, since we have two manifolds, the Riemannian connection of N1 I will denote by delta dash, and delta double dash denotes the Riemannian connection on the second factor N2. And the relationship which is known already, Vional has found these relationships, delta U1 V1 equal to this much, where delta double dash ln F2 is known. Similarly, formula number 12 is obtained for these W warp products. We have several formulas which are already known. Del ln F is defined by this relationship, del G of del ln F U equal to U ln F. Okay, so the first observation is that if you have a W warp product manifold with matrix, this W warp product matrix, then N1 product Q is a point on the second factor, and the fibers P product N2, where P is a point in N1, are totally umbilical. Both these submanifolds are totally umbilical for all points P and Q. Whereas the leaf N1 product Q and is totally Jauresic, and gradient restricted to N2. F2 is 0. Similarly, the fiber is totally Jauresic when the gradient is restricted to F1. There are a few more formulas that we have obtained here. And then this proposition gives us some relationship of second fundamental form. It only tells where U1, U2, U1, V1, etc. will always denote the vector field tangential to the first factor. U2, V2, etc. they will denote vector field along the second factor. So we observe that these relationships are satisfied by the second fundamental form. These relationship will be used in our subsequent discussions. So the first lemma that we have is this. We have a warp product, doubly warp product submanifold of a Kenmotsu manifold with one of the factors of phi anti-invariant. That is a special thing, that we are taking our second factor to be phi anti-invariant submanifold. Then we have this formula. U1 lin F1 is eta U1 and U2 lin F2 is eta U2. So if U1 lin F1 is eta U1 if N1 is a phi anti-invariant, and U2 lin F2 equal to eta U2 if N2 is phi anti-invariant. So these are some observations. And as a consequence of the above lemma, we deduce a theorem. In fact, not only this, there are many other things which we used in proving the following theorem. There does not exist a non-trivial doubly warp-product submanifold of a Kenmotsu manifold normal to the structure vector field xi. So this case, when xi is normal to the submanifold, the existence of a non-trivial doubly warp product is ruled out. So we led to only some manifolds which are tangential to the structure vector field xi. Only these manifolds can be studied, some manifolds. Now, it is observed that if xi1 and xi2 are denote the component, if it is not completely normal, xi is not completely normal, then it will have components. So if xi1 and xi2 are the components of xi along n1 and n2, and if xi1 and xi2 are both non-zero, then del n1 is along xi1 and del in f2 is along xi2. This is the observation that we made from the last theorem. In particular, if xi lies completely along one of the factors of M, then we have the following cases that appear automatically. If xi2 is 0, then any equation, then an equation obtained in the proof of the last theorem, del in f2 is 0. That is, f2 is constant along n2. Similarly, if xi1 is 0, then by one of the equations that we obtained in the proof, tells us that del in f1 is 0, which means f1 is constant along n1. And now the above, all these findings can be summarized into a theorem over here. So this is a theorem which summarizes the previous results. It says that if M is a doubly warped X, some manifold of a Kenmotsu manifold M bar, such that the structure vector field xi is tangent to M. If xi has a non-trivial components along n1 and n2, then M is simply a Riemannian product of n1 and n2. Okay, and that is a trivial warp product. However, if xi is tangent to the first factor of M, then f2 is constant. Whereas if xi is tangent to n2, then f1 is constant. So we led to only some manifolds where xi is either tangent to n1 or n2. So it says that there does not exist a non-trivial doubly warp product submanifold of a Kenmotsu manifold tangent to the structure vector field. So keep in mind, not only we are ruling pseudo-slant warp product, we are ruling out all W warp products of manifold, existence of all W warp products of manifold inside Kenmotsu manifold. We have taken all these things case by case. All right, so the last section is the warp products of manifolds of a Kenmotsu manifolds with one of the factors of phi anti-invariant submanifold. This is an important case that we wanted to deal with separately. So in view of the theorem that we did in our last section, W warp products of manifolds of Kenmotsu manifold are trivial. That is, in this case, either f1 or f2 is constant. So we can consider only single warp product. Therefore, the only warp products in a Kenmotsu manifold are single warp products with the structure vector field xi tangent to the submanifold. The possibility of xi being normal to the submanifold has already been ruled out. Okay. So now we have certain formulas. There does not exist a single non-trivial doubly warp product sorry, single non-trivial warp product manifold of a Kenmotsu manifold such that the structure vector field I is tangential to the second vector. Not only that, we have also ruled out the case when xi is tangential to the second vector. I mean, if you consider a single warp product, then your xi has to be tangential to the first vector. This is one of the important observations. All right. So this is what we have written. There does not exist a single non-trivial warp product submanifold of a Kenmotsu manifold such that the structure vector field xi is tangential to the second factor of the submanifold. Has the possible non-trivial warp product submanifold M of a Kenmotsu manifold has the form N1 product Fn2 with the structure vector field xi tangential to N1. So this is the form that an existent warp product submanifold will have. And therefore, the formula on this submanifold reduced to this, given by equation number 20. And the second fundamental form inside M. So this will be sigma 2 U2 is this. And which also tells you that this is second factor is in fact totally umbilical in M, the submanifold M. And not only this, we have got hold of the warping function f. According to this proposition, if n1 product fn2 be a warp product submanifold of a Kenmotsu manifold, if the structure vector field xi I am taking as del upon del t, then the warping function satisfies ft equal to e to the power t. So now, the other cases are taken up. These cases, let me wind up because my time. So we have obtained some formula with shape operator and second fundamental form as well. And there are some other formulas which we have obtained for the remaining case. So pseudo-Slant submanifold and Kenmotsu manifold are a special case of submanifold admitting phi and t invariant distribution. Our aim in the remainder part of the section is to study these submanifold. And for these submanifold, we have obtained these formulas. So I hope the time is over, so I have to wind it up. But before winding up, let me tell you the final result. A proper point-wise pseudo-Slant submanifold M1 of a Kenmotsu manifold is a warp product submanifold of this type. If and only if the function mu on M1 with x mu equal to 0 for all x in D satisfies this. And there are examples that we have discussed for both the cases. And I stop at this point, and there are some references as well. We have some more observations. So we have some example and then references. Okay, because I have taken perhaps more than stipulated time, so I stop and thank you for your kind attention.